Hello dear friends, welcome to my channel. Today's discussions is quantum field theory. So friends, before these discussions, we need to know what is quantum field theory. So we need to go some de Broglie wavelength we need to know and Compton wavelength. Okay. So Dirac argument for antiparticles later together with the better understanding that we get viewing particles in the framework of quantum field theory. We will quick, quickly sketch the circumstances in which we expect the number of particles to charge. Consider a particle of mass m trapped in a box of size L. Heisenberg tells us that the uncertainty in the momentum is del p obviously greater than equals to h bar divided by capital L. In a relativistic setting, momentum and energy are on equivalent footing, so we should also have a uncertainty in the energy of the del A greater than equals to hc divided by L. However, when the uncertainty in the energy exceeds del E equals to 2m c square, okay, we cross the barrier to pop particle antiparticle pairs out of the vacuum. We learn the particle antiparticle pairs are expected to be important when a particle of mass m is localized within a distance of order lambda equals to h bar. H bar means Planck constant. Okay, Planck constant is h and h bar is equal to h divided by 2 pi. Okay, h divided by 2 pi mc. At distance shorter than this, there is a high probability that we will detect particle antiparticle pairs swarming around the original particle that we put in. The distance lambda is called Compton wavelength. It is always smaller than the de Broglie wavelength. Lambda dB is equal to h divided by mod of p for momentum. If you like, the de Broglie wavelength is the distance at which the wave-like nature of particles becomes apparent. The Compton wavelength is the distance at which the concept of a single point-like particle breaks down completely. The presence of multitude of particles and antiparticles at short distance tells us that any attempt to write down a relativistic version of the one particle Schrodinger equations is doomed to failure. Okay, there is no mechanisms in standard non-relativistic quantum mechanics to deal. Okay, quantum mechanics to deal with changes in the particle number. Indeed, any attempt to naively construct okay, so danger equation meets the serious problems. Okay, so we have already discussed that the Compton wavelength is the distance at which the concept of a single point like particle breaks down completely. Okay, the presence multitude of particles and antiparticles at short distance tells us that any attempt to write down relativistic version of the one particle Schrodinger equations is deemed to failure. Okay, I have already told. Now there is no mechanism in standard non-relativistic quantum mechanics to deal with changes in the particle number. Indeed, any attempt to naively construct a relativistic version of the one particle Schrodinger equation meets with serious problems. In each case, the failure is telling us that once we enter the relativistic regime, we need a new formalisms in order to treat state with an unspecific number of particles. This formalisms is quantum field theory. Okay, so now that this sounds that okay, all particles of the same type of the same. Okay, now it is the another factor, what is quantum field theory. Having told you why quantum field theory is necessary, i I should really tell you what it is. The clue is in the name. It is quantizations of a classical field. The most familiar example of which is electromagnetic field. In standard quantum mechanisms, we are taught to take the classical degree of freedom and promote them to operators acting on a Hilbert space. The rules for quantizing a field are no different. Thus, the basic degree of freedom in quantum field theory are operator valued function of space and time. This means that we are dealing with an infinite number of degrees of freedom, at least one for every point in space. This infinity will come back to beat on several occasions. Okay, so now we will tell another examples, another definitions, that what is quantum field theorem, another definitions, because it is the quantum field theorem good or not. Another definitions is that the the sound rather dumb, but it is not. What I mean by this is that two electrons are identically in every way, regardless of where they came from, what they have been through. The same is true of every other fundamental particles. Let me illustrate this through a rather prosaic story. Suppose we capture a photon from a cosmic ray, which we identify as coming from supernova lying 8 billion light years away. We compare this proton with one freshly minted in a particle accelerations here on Earth, and the two are exactly the same. How is this possible? Why are not there errors in proton productions? How can two objects manufactured so far apart in space and time be identical in all respects? One explanation that might be offered is that there is a sea of proton stuff filling the universe, and when we make a proton, we somehow dip our hand into the stuff and form into mold a proton. Then it is not surprising the protons produced in different parts of the universe are identical. They are made of the same stuff. It turns out that this is roughly what happens. The stuff is proton field, or if you look closely enough, the quark field. In fact, there more to this tale. Being the same in the quantum world is not like the same in the classical world, quantum particles that are the same are truly indistinguishable. Swapping two particles around leaves the state completely unchanged. Apart from the possible minus sign, the minus sign determines the statistics of the particle. In quantum mechanics, you have to put the statistics in by hand, and to agree with experiment should choose both statistics of for integer spin particles, Fermi statistics, half integer spin particles. In quantum field theory, this relationship between spin and statistics is not something that you have to put in by hand. Rather, it is consequence of the framework. So, friends, I have already told what is the quantum field theory and quantum field theory is good or not. Okay. So now I will go to discuss the classical field theory. Okay, what is field? A field is quantity defined at every point of space and time, while classical particle mechanics deals with a finite number of generalized coordinate. Okay, electric field, you know already what is electric field, the Lagrangian, you also know that what is Lagrangian in my classical mechanics. Okay, but in here I have already discussed Klein Gordon equations. Now friends, we go to the potential energy of the field. This is the potential energy of the field. Okay, this equation V is equal to d cube x half into del phi square plus half m square phi square. This first term in this expression is called gradient energy. Okay, first term is called gradient energy, and while the phrase potential energy, potential is usually reserved for the last term. To determine the equation of motion, so we get del L by del phi minus m square phi, and del L divided by del into del mu phi equal to del mu phi minus phi dot minus del phi. Okay, so Euler Lagrange equation is equal to phi double dot del square phi plus m square phi equals to 0. This is Klein Gordon equations. Okay friends, I have already created, and it can be written as del mu plus m square phi. Okay, so it is the Klein Gordon equations. You know that Laplace Minkowski space is sometimes denoted a rectangle. Okay, so Klein Gordon equation is rectangle phi plus m square phi. Okay, no problem. So you know, and another factor is L equals to this is the equation Lagrangian potential. Above generalizations of the Klein Gordon equations comes from considering the Lagrangian with arbitrary potential v phi. Okay, so another example, first order Lagrangians. Okay, now I discuss first order Lagrangians. Okay, Lagrangian examples, Lagrangian equations. Okay, so first order Lagrangian, L is equal to psi star I psi star minus psi and del psi. Okay, this equation you will get from my Klein Gordon equations. I will give also link in here. Please check how to derive it. Now you see that the equations, we can determine the equations of motion in treating psi and psi star as independent objects. This gives us the equation of motion del square psi plus m psi. This looks very much like a Schrodinger equations, except is in not. So the initial data required on a Cauchy surface differs for the two examples above, and when L proportional to phi dot square, both phi and phi dot must be specified to determine the future evolutions. Okay, so Lagrangian equation I just discussed. So Maxwell equations. Okay, So Maxwell equation is, this is the max. So friends, Maxwell equations in the vacuum from the Lagrangian L is equal to half into del mu a mu plus half into del mu a mu whole square. So friends, notice the minus signs. This is okay. This minus sign. This is to ensure that the kinetic terms for AI are positive using mean Kowalski space metric. L is proportional to half into A dot whole square. Okay. So the Lagrangian has no kinetic term A dot whole square or for A0. We will see the consequence. Okay. So we will see this equation, and which may derive the equations of this, where the field strength is defined F mu nu. Okay. F mu nu is equal to del mu into a mu and del mu a mu. So Maxwell equation in a vacuum, del dot E equals to 0. So del E divided by the del T is equal to del cross B. Okay, so you know this equation. Okay, and this equation you can get also in my channel, and also video, means short video I have already loaded the Maxwell equations. So Maxwell Lagrangian is L is equal to minus 1 by 4 f mu nu. So this is very easy, because this is subscript f subscript mu nu and f super subscript mu nu. Okay, del subscript mu, f subscript super subscript mu nu. Okay, so all the subscript and super subscript, you, I think that you know, because I have already discussed it in my differential geometry. Now locality and locality. Okay, so Lagrangian is local. Okay, Lagrangian is local. This means that there are no terms in the Lagrangian coupling phi x comma t directly to phi y comma t. X bar does not equals to y bar. For example, there are no terms that looks. Okay, so this way I can write Lagrangian. So a priori there is no reason. After all, X bar is merely a label. We are quite happy to couple other labels together. Del 3 A0, del 0 A3 in the Maxwell Lagrangian couples, and mu equals to 0 field and mu equals to 3 field. But the closest we get for the X bar, the coupling link between f phi x bar and phi x bar plus del x through the gradient term del phi whole square. This property of locality is, as far as we know, a key features of all theories of nature. Indeed, one of the main reasons introducing field theories in classical physics is to implement locality. In this course, we will only consider local Lagrangian. Now friends, we discuss Lorentz invariant. The laws of nature are and one of the main motivations to develop quantum field theory is to reconcile quantum mechanics with special relativity. To this end, we want to construct field theories in which space and time. Okay, reconcile. So quantum field theory is to reconcile quantum mechanics with special relativity. To this end, we want to construct field theories in which space and time are placed on the equal footing. The theory is invariant under Lorentz transformation. So x superscript mu is equal to x dash superscript mu lambda del mu nu del lambda superscript mu subscript nu x superscript mu, where del mu nu means is equal to is act as a tensor. Okay, del mu nu and Minkowski tensor. Okay, this is the act as a tensor. Okay, so del mu nu is equal to can be written this way, del mu nu, and where gamma is equal to 1 by root over 1 minus v square. The Lorentz transformation form a Lie group under matrix multiplications. Okay, so symmetric and particle physics course. You will learn more about this in the symmetric and particle physics course. Then Lorentz transformations form a Lie group under matrix multiplications. Okay, so the Lorentz transformation has a representations on the fields. The simplest example is the scalar field which under the Lorentz transformations x tends to del x transforms as. Okay, so a remembering point that symmetric particle physics you can understand Lie group under matrix multiplications. Okay, so Lorentz transformations. Okay, so Lorentz transformation, the inverse nabla inverse appears the argument because we are dealing. Okay, phi x is equal to phi dash x. Phi dash x is equal to phi lambda capital lambda inverse x. So lambda inverse x, the inverse lambda inverse appears the argument because we are dealing with the active transformation in which the field is truly shifted. To see why this means that the inverse appears, it will shift to consider non-relativistic examples such as a temperature field. And suppose we start with an initial field phi x vector which has a hotspot, say x vector is equal to 1 0 comma 0, and after a rotation x vector is 0 comma 1 comma 0. Ask what the old field looked like where we have come from the r inverse 0 1 comma 0 equal to 1 0 0. This r inverse is the origin of the inverse transformations. If we were instead dealing with a passive transformation in which we relabel our choice of coordinates, we would have instead phi x is equal to phi dash x is equal to phi lambda capital lambda x. The definitions of Lorentz invariant theory is the phi x solves the equation of motions, then phi lambda inverse as solves the equations of motion. We can ensure that this property holds by requiring that the action of Lorentz invariant. Let's look at our example, the Klein-Gordon equations. I am already deriving this equation in my Klein-Gordon equation, the Lorentz transformations. Okay, please check my derivations. Phi x is equal to phi dash x. So this equation derivations, we get this in this equation, and after that we get Lagrangian identity, and next we get this value. Okay, so this is the equations, and the potential terms transforms in the same way. Phi square x is equal to phi square y. Putting this all together, we find that the action is indeed invariant under the Lorentz transformations. S equals to d to the power 4 lx, L d to the power 4 ly, and d to the power 4 ly is equal to S. So where in the last step we need the fact that we don't pick up okay pick up a Jacobian factor when we change integration variables from d4x to d4y. This follows because det lambda is equal to 1. At least the Lorentz transformations connected to identity, which for now is all we deal with. First order dynamics. So friends, you all have already known the Maxwell equations. Maxwell equations under the Lorentz transformation, you can check the Maxwell Lagrangian, okay, in the equation 1.21. So equation 1.21 I have already discussed that what is the equation 1.21 in this equation is L is equal to 1 by 4 f mu nu f subscript mu nu and f superscript mu nu. This is the Lagrangian, these equations. So Lorentz invariant. So another factor is the no either theorem. No either theorem I have already discussed in my Klein-Gordon equations video. So here I just you will check that every continuous symmetric Lagrangian gives the conserved current J superscript mu x, and the equation of the motions imply, in other words, del mu j mu is equal to 0. Okay, this is the equations. Okay, no either theorem, current electricity. So d cube x is equal to j0. And repeating the analysis above, we find that this is the another equations. Okay, so let's go. A are the area bounding V. We have the Stokes theorem. These equations means that any change leaving V must be accounted for by a flow of a current C vector J out of the volume. This kind of local conservations of charge holds in any local field theory. Okay, so this is my equations, and another examples is energy momentum tensors. Okay, energy momentum tensor is equal to T mu nu. This is the equations, and this is the E is equal to this formula. This is the del mu 2 mu is equal to 0. Energy conservation energy and momentum, and we get these equations. This is the energy, and t superscript mu nu comes out symmetric. This is this equation equals holds, and message that energy momentum tensor and theory symmetric, adding the extra term. And capital theta mu nu is equal to t mu del rho and gamma superscript rho mu nu. So whatever you see, that gamma rho mu nu is equal to superscript and minus, both are antisymmetric matrix, so it is 0. So new energy momentum tensor is the conserved current. And a cute trick, one reasons that you may want to symmetric energy momentum tensor is to make contact with general relativity. Such an object's height on the right band side of Einstein field equation. In fact, the observation provides quick and easy way to determine the symmetric energy momentum tensors. Firstly, consider coupling the theory to a curved background space-time, introducing an arbitrary matrix G mu nu subscript G mu nu x in place of eta mu nu, and replacing the kinetic terms with suitable covariant derivatives using minimal coupling. Okay, using minimal coupling, then the symmetric energy momentum tensor flat space theory is given. So this is the flat space theory. It should be noted, however, that the trick requires a little more care when working. with spinors. Okay friends, I hope that I give some idea about the quantum field